So, continuing with our session on numerical problems in process metallurgy, I would now like to advance a step further and address today problems related to reaction kinetics. And as you all know that you have read transport phenomena, iron making, steel making. I mean metallurgical processes like those with which we are concerned with reduction of oxides, oxidation of metals, etc. We have both mass transfer as well as chemical reaction as the kinetic steps. So, I wish to demonstrate through today's problem solving session that for various rate limiting kinetic steps, how would we proceed to estimate the corresponding rates. And to illustrate the various calculation schemes, let me pose a problem. So, what I am saying is that I have a nickel oxide sphere, and as I go on discussing the problem, I will also explain very briefly the relevant underlying physics, so that you can revise your fundamentals. So, this is a nickel oxide solid sphere. So, I am posing the problem for you and then we will solve the problem. So, this is a solid sphere, and this solid sphere is undergoing reduction in a gas mixture. So, basically the chemical reaction that is taking place is H2 gas, and this is nickel solid and H2O gas. The process is carried out at 1 atmosphere pressure, total pressure is 1 atmosphere, and we have temperature at which the reduction reaction is occurring is 700 degrees centigrade or 973 Kelvin, 973 Kelvin. So, at a time t is equal to 0, when the process just starts, so you can visualize that there is a furnace here. It is a tube furnace. The cross section of the furnace is a circular cross section. So, it is a hollow cylindrical tube. So, we have a sphere of the nickel oxide ore, and here we pass the gas mixture, and the entire thing is 973. And this is our solid nickel sphere. So, typical thermogravimetric setup that we have. So, at time t is equal to 0, the entire sphere and the diameter of the sphere, let us say diameter of the solid is 0.01, it is 1 centimeter. So, 1 meter, and we are dealing everything in SI unit. So, this is the scenario. The reaction interface is here, and this reaction takes place at time t greater than 0. The reaction interface moves inside the radial coordinate, and this is the position at time t is equal to 0. So, the gas comes, reaches the surface, and then it diffuses through the solid, and so this is now reduced already. So, this is nickel and this is nickel oxide, and then the gas diffuses through the nickel, reaches at this interface where the same reaction takes place. Now, as far as this problem is concerned, we can have this is you must be knowing this from your basic knowledge of kinetics, that there is a boundary layer, concentration boundary layer, which can be the rate determining transport through the concentration boundary layer, could be the rate limiting step, or the transport through the diffusion, diffusion through the solid porous nickel could be rate limiting, or the chemical reaction which is taking place at the interface, because you can resolve the entire process, although you look at it as chemical reaction, into 5 different kinetic steps. Okay? And this you must be knowing. I am not going to keep on describing this again and again. So, boundary layer transport, then the series step is the diffusion through the solid, then the interfacial chemical reaction, then the product gas evolves and the product gas follows a reverse path. It diffuses through the solid porous nickel layer and then it diffuses to the boundary layer and then the process is complete. Okay? And of these 5 kinetic steps, one could be rate controlling, more than one steps could be rate controlling, and we can say there is a possibility that the process is either mass transfer controlled or chemically controlled or mixed controlled. And I want to now demonstrate through these problems, depending on the rate limiting step or the nature of the rate limiting step, how the mathematical treatment would vary. Case 1. When transport through the boundary layer is the rate limiting. Transport through boundary layer, this essential element concentration boundary layer is rate limiting. That means all other steps can be considered to be infinitely fast, so therefore non-existent. The entire reduction process can be characterized in terms of one single kinetic step, and that is the transport across the boundary layer is rate limiting. Now let us give some data, okay, before we solve the problem. Some data has already been given, okay. So it is said that the gas flow rate Q of the mixture is given also, and the value of this is 13.6 into 10 to the power minus 6 normal meter cube per second. You must understand that this is not the gas flow rate that the particle sees. The particle sees a much higher gas velocity or gas volume metric flow rate because of the thermal expansion. So, if we can consider an ideal gas behavior, actual gas flow rate would be this value multiplied by 973 divided by 298. Okay. So, if it is normal, okay, standard is 273, but if it is normal, that means we know it is 25 degree centigrade. So, it is 298. So, according to ideal gas flow, you can jack up the volume which actually the particle is facing, and based on this, then the normal meter cube per second flow rate, you should be able to calculate that what is the velocity. So, the volumetric flow rate is given to you. The density of the mixture at 700 degree centigrade is also given to you, and that is 0.22 kg per meter cube. The viscosity of the mixture is also given to you 700 degree centigrade, and this is the value is viscosity is something like here, okay, let me see, 2.25 into 10 to the power minus 5 again in kg meter second, and diffusion coefficient of H2H2O mixture through the gaseous mixture, okay, is 7.1 into 10 to the power minus 4 meter square per second. So, these are the data which is, and now I want to calculate the rate of transport or the rate of reduction of nickel oxide, and you must look at this equation and immediately say that 1 mole of nickel oxide, if for every mole of hydrogen transporting through the boundary layer, 1 mole of nickel oxide so gets reduced. So, there is a equivalence of on a 1:1 basis. So, if you calculate the molar, if you can calculate the molar rate of diffusion of nitrogen transport of nitrogen through the boundary layer, that in essence becomes equal to the molar rate of reduction of nickel oxide, which is dictated by the stoichiometry of this particular equation. So, with this data, now we want to calculate the rate. So, this is when the transport, calculate the rate of nickel oxide reduction when transport of hydrogen gas through the boundary layer is rate limiting kinetic step. So, now we have to apply our theoretical knowledge to solve this problem. The boundary layer mass transfer theory tells us that the rate of transport is equal to area multiplied by mass transfer coefficient multiplied by the concentration difference. So, CH2 in bulk minus CH2 at the interface. Now, whether the interface is here or whether the interface is here, it really does not matter, because per se the diffusion does not exist, which essentially means this and this concentration, these two concentrations are essentially identical, okay? Because the diffusion under the assumption has been assumed to be non-existent, it is not influencing the rate. So, therefore, the resistance offered by diffusion does not exist. So, there is no concentration difference across the boundary layer. So, therefore, this concentration can be assumed to be prevailing right up to the boundary layer and solid interface here, and it is this concentration that actually drives, that is embedded in this particular, the concentration difference across the boundary layer. Also, we must understand that this concentration at the true reacting interface, okay, whether it is here or here, the concentration of the gas at the reaction interface is dictated by the equilibrium, can be obtained on the basis of equilibrium of the chemical reaction. Why equilibrium? Because the chemical reaction is also very fast. So, therefore, any fast process would reach equilibrium quickly. So, therefore, diffusion process can be considered to be at equilibrium. Okay? Chemical reduction process, reduction reaction can be assumed to be under equilibrium, and these assumptions will allow us to specify the concentration difference that drives the boundary layer mass transfer. Now, this is, as I said, this is molar rate. So, I would say this is kg mole per second. So, therefore, the concentrations here must also be kg moles per meter cube, that is the unit in which you use the concentration. And we can now convert this into, using the ideal gas law, as pH2 B minus pH2 interface. Okay. PV is equal to nRT, or P is equal to P by RT is equal to N by number of moles divided by volume, which is kg moles per meter cube. Okay. It is also given that the bulk concentration, this mixture, I know at what is the mixture value, okay, what is the ratio of the concentration. So, we say that pH2 H2 H2O ratio, pH2 pH2O ratio in the bulk, this is given in the problem as a data, is equal to 9. And this essentially tells us that we will say that 90% is H2O. So, therefore, we can say that pH2 is roughly is equal to bulk on the basis of this, because this is there, total atmosphere, 2 equation 2 unknown, we solve it and then we find out that this is equal to 0.1. Also, it is given that at this particular interface, or the equilibrium value corresponding to this, pH2O by pH2 at the interface is equal to 100. These values are given. This value can be obtained easily. We know that the moment we put delta G naught is equal to minus RT ln K, we will get pH2O by pH2, because this is activity of nickel oxide is solid 1, activity of nickel, pure nickel is 1. So, therefore, pH2 ratio can be obtained from the standard free energy change value, and noting that the total pressure is 1, I can find out. To save some time, so these values have been directly provided to you rather than asking you to calculate the equilibrium on the basis of this reaction, because the temperature is also specified. So, one can really calculate. So, these values are given, and this essentially means that pH2 in the interface is 0.01. If you solve it again with two equations, pH2 plus pH2O is equal to 1, pH2 plus pH2O is equal to 1 and pH2O divided by pH2 is equal to 100, then the interfacial partial pressure of hydrogen comes out to be 0.1 and the delta value corresponding which is embodied in this equation comes out to be 0.09. So, therefore, we understand that this value has been calculated 0.09, R is known to us 82.06 into 10 to the power minus 3 and this is atmosphere kg mole Kelvin. So, the value is R value atmosphere kg mole. Okay. I think it is there is a meter cube also here, meter cube atmosphere, yes. So, this Kelvin will cancel out, okay. We will be left with this becomes meter cube per second. So, this meter cube will be cancelled out, atmosphere will be cancelled out, okay, and then we will be left Kelvin will cancel out. We are going to leave from this in terms of kg mole per second. That is the unit of this parameter is going to come. So, we can calculate A is equal to 4 pi r square, r sphere square, and that is given to us because the diameter of the sphere is this. So, therefore, the radius of the sphere is 4 pi into 0.005 square. Only one thing now we need, the moment we can calculate the value of Km, the mass transfer coefficient, the problem is solved because all other parameters are 9, just punch in the keys in your calculator and get the values out. Okay. Where from Km is going to be obtained. Now, this is for boundary layer mass transfer problems. So, the flow past a solid sphere, in that case we have standard correlations that you also must be knowing, and because it is a spherical geometry. So, we will have the popular correlation, that is the Range Marshal correlation, which will give us Sherwood's number is equal to 2 plus 0.6 into Reynolds number, that is the diameter based Reynolds number, and Schmidt number raised to the power 1 by 3, where Sherwood's number, as you all know, is equal to diameter based Sherwood's number is nothing but Km, mass transfer coefficient, multiplied by the diameter of the sphere divided by the diffusion coefficient of the mixture dH2H2O. So, we can calculate Reynolds number. How the Reynolds number can be calculated? The Reynolds number can be calculated, for example, Reynolds number is equal to, and this is the particle Reynolds number, okay, particle diameter based Reynolds number. So, this is diameter of the sphere multiplied by rho mixture, mu mixture, and then the velocity past the sphere. The velocity information is dictated here, and as I have indicated, the velocity is nothing but volumetric flow rate by cross sectional area d tube square multiplied by 973 divided by 298. Temperature correction according to the ideal gas law. This is volumetric flow rate by cross sectional area, that gives us the velocity, and if you put this velocity now, you are going to get, put this flow rate values now, and you are going to get the velocity value, which will come out to be in terms of meters per second. And if you substitute the value, Q is equal to 13.6 into 10 to the power minus 6, diameter of the tube, which is 5 centimeter or 0.05, this is 0.05 meter. So, everything else is known, and the value of V thus calculated will come out to be I will not put here. So, the value of V will come out to be, if you substitute the values here, it is 2.414 into 10 to the power minus 2 meters per second. I have given you the diameter of the sphere, rho mixture has been given to you, velocity just now I have calculated, mu mixture is also given to you. So, if I substitute now, okay, that is 0.01, which is the diameter of the sphere, rho mixture is 0.22, velocity is 2.414 into 10 to the power minus 2, and then mu mixture is also given to you as 2.25 into 10 to the power minus 5, and then the Reynolds number, which is a dimensionless quantity, it comes out to be equal to 2 point something. Schmidt number is this, and 2.38. Similarly, I can say that we can calculate the Schmidt number which appears in this correlation. So, we have calculated Reynolds number. Now, we need to calculate Schmidt number, so that we can calculate Sherwood's number, and on the basis of Sherwood's number then we will be able to calculate mass transfer coefficient Km, and that is it. We just plug in the values and get the result, and Schmidt number in this particular case is the kinematic viscosity divided by diffusion coefficient, and the kinematic viscosity value is nothing but mu by rho. So, mu mixture, okay, rho mixture, and then d mixture. And if you substitute all the values, the value of Schmidt number will come out to be 0.143. Plugging in this value, that is the Reynolds number value, plugging in the Schmidt number value into this equation, or the solid liquid mass transfer correlations, we can calculate the Sherwood's number, and then from this we can calculate the mass transfer coefficient Km, and that mass transfer coefficient value will come out to be, what is that, 0.174. meters per second. That is the value of the mass transfer coefficient. So, therefore, now we can substitute the values here. So, let me just, so this is our expression that we have written here. So, therefore, we can say area, okay, and that area has been calculated, okay, 4 pi surface area 4 pi r square 0.005 squared, then 82.06 into 10 to the power minus 3. Then we have temperature RT, okay, and that temperature is 973. Then we have mass transfer coefficient, that mass transfer coefficient is 0.174, and then multiplied by the concentration difference in terms of the partial pressure, and that is equal to 0.09. And as I have indicated that this expression, okay, on the basis of this equation will give you kg mole of hydrogen per second. That is the rate of transport of kg mole, and this value is essentially equal to kg mole of nickel oxide per second. So, that is essentially the rate of reaction, and if you substitute the value, okay, you get an answer which is 6.18 into 10 to the power minus 8 kg moles per second. And you can convert it, of course, into kg of nickel oxide by simply using its molecular weight. Okay. So, this is the case 1 when transport across the phase concentration boundary layer was assumed to be the rate limiting step. Now, let me erase a part of the work, and then the problem still remains the same. Particle is suspended, gas is flowing, flow past, okay, the gas is contains enough reducing agent hydrogen gas to drive this reaction in the forward direction. But now case 2 we want to do it when diffusion across the porous layer is the rate limiting kinetic step, that is the second step. So, for us now we still consider the chemical reaction to be at equilibrium. Now, the first case does not exist, that means the transport through the boundary layer does not exist. And what does that essentially indicate? That indicates the concentration which is here is instantaneously available right up to this particular interface. There is no concentration difference between the width of the boundary layer. If the transport across, if there is no concentration difference, the transport is instantaneous. Okay? So, therefore, it is not controlling the rate at all. So, that prevalent concentration of pH 2 by pH 2, which is given to be 9, which is prevalent here or which is prevalent here or which is prevalent here, can be assumed to be present right up to the surface of the solid, and this it will prevail right up to here, simply because we have assumed that diffusion through the concentration boundary layer is the rate limiting step. So, let us pose the problem. These values are not going to be important for us. One issue needs a little consideration here. I want to revise you that this is the transport across the boundary layer. It shows you that the rate of reduction is independent of the time. There is no because the boundary layer thickness is determined by the fluid flow conditions, and so long as the flow characteristics or the velocity remains constant, the characteristics of the thickness does not change. So, therefore, at all time the rate is constant or rate is invariant of temperature time. On the other hand, when you assume case 2, that is diffusion across the porous nickel layer is rate limiting. So, now we have case 2, diffusion across porous nickel layer. You know why I write porous, that should be clear to you. Nickel layer as rate limiting. All other kinetic steps are assumed to be infinitely fast. In that case, you must understand, as time goes on, this reaction front keeps on moving towards the center. Okay? The nickel core, nickel oxide core shrinks as a function of time. That means the path of diffusion is changing as a function of time. So, if diffusion through porous nickel layer is rate limiting, and that the porous nickel layer is growing as a function of time, this essentially this essentially tells us that the rate of reduction is going to be a time dependent phenomena. If I measure the rate of reduction at 10 seconds and 20 seconds, they will not be same, simply because of the fact that the path of reduction reaction is changing as a function of time. So, therefore, we have to specify that the problem is now all the data remains the same, whatever I have provided, but I am now giving calculate the rate with this kinetic step as the rate limiting step, calculate the rate of reduction when the fraction transformed is 0.5. You must remember, at time t is equal to 0, fraction transformed is 0, nothing is transformed. On the other hand, fraction transformed becomes, when reduction is complete, fraction transport becomes equal to 1, there is no residual nickel oxide left. So, the entire solid has become now porous nickel. So, what is the fraction transformed? Fraction transformed is defined as 1 minus Ri. So, we will say that this is the outer radius. So, and this is, that is what it is. How we this comes out, because you see you have so let us see. No, let me write it down, fraction transform. So, we have initially 4 by 3 pi at, okay, I say R outer, which is same as R sphere. R outer is equal to R sphere. Into density. Now, we have 4 by 3 pi R I cube, okay, into rho, and this is 4 by 3, assuming that the density of nickel and nickel oxide are not largely changing for mathematical simplicity. So, this essentially tells us the amount of nickel oxide which is present. This Ri is changing as a function of time. So, therefore, the value of F pertains to that instantaneous value of Ri, okay? And it is based on this that I have gotten 1 divided by Ri by R0. So, therefore, I can say given the constraint we have Ri is equal to 1 minus F, okay, and therefore, Ri is equal to radius of the is 0.5 raised to the power 1 by 3 . So, this is so that comes out to be so this diameter now, this is radius is initially this value. So, let me just use a different color chalk, so that you can. So, this is the initial radius, so which is 0.005, and now I want you to calculate that when the radius has fallen to 0.0394, and this value of radius corresponds to F is equal to the fraction transformed is equal to 0.5. I want you to calculate the rate of reduction. So, when the radius is here much smaller than this value, the rate of reduction is not going to be identical. The rate of reduction for diffusion is the rate limiting step. Okay. So, this gives us a very interesting observation that suppose if you are doing experimental studies, okay, you find that rate of reduction is not changing, whether you measure it at 10 seconds, 20 seconds, 2 minutes, 5 minutes, the rate of reduction is constant. This possibly gives you an idea that look, possibly diffusion is not a very important kinetic steps in the whole scenario. Okay. So, when you solve problems, we must understand that it carries certain messages, and we have to get those messages out, while solving the problem, and that is, the learning process actually, not just mechanically getting to the answer is the issue at this particular moment. So, we have found out that, so R0 we have the outer radius or the radius of the sphere is 0.005 meter, Ri which is a function of time, okay, and 0.005, 0.0394. This is the values that we have derived. Density etc., other diameter remains constant. Now, we can apply our knowledge of that you have studied. Okay. So, the problem becomes now is a spherical nickel oxide ore particle. So, you can now imagine there is a concentric spherical shell, okay, and one is Ri, one is R0, okay, and that is what is, this is R outer and this is R inner, and we know that the rate of transport through a spherical shell, the classical problem that we solve from the Fick's second law or the mass balance equation. So, this if you solve this equation 1 by r square differential d r square dc dr is equal to 0 and apply the boundary conditions, that at two boundary conditions are needed, at r is equal to Ri and at r is equal to R0, C is equal to C0 and this is C is equal to Ci, and in this case what we are talking about is the diffusion of hydrogen. So, I am not writing, this essentially represents the concentration of hydrogen, okay, and in terms of appropriate units, concentration of hydrogen at the outer, right here, at the outer radius. This essentially represents the concentration of hydrogen at the inner radius, that is what it is. Okay. Now, this concentration we have figured out, this concentration is same as the bulk concentration, as I have said in the beginning itself. The concentration right here is again continue to be the equilibrium concentration, because it is dictated by the chemical reaction. Okay. So, at this particular point, okay, if the chemical reaction is in equilibrium, because the chemical reaction is very fast, diffusion is the rate limiting step. So, therefore, we can fix the concentration here to be the equilibrium concentration. So, the concentration differential essentially remains the same as the previous problem, very interesting consequence actually. So, we can solve this equation and then we can find out the net rate of transport, and as far as this equation, the net rate of transport is given in terms of 4 pi d is the diffusion coefficient, R0 Ri and R0 minus Ri multiplied by, if we write in terms of partial pressure, then we will say partial pressure of hydrogen in the bulk minus partial pressure of hydrogen in the equilibrium at the interface, and because we have used partial pressure, I will divide it by RT. That is what is that. Now, we must understand that the original equation, when it takes the diffusion was in this particular direction. Okay. So, the concentration difference was higher, concentration was higher here, the concentration is lower here. So, the original derivation appeared with a negative sign, but I have changed it otherwise, because the diffusion is taking place in the reverse direction, the concentration is higher here and the concentration is lower here, and that is why. So, if you look at the classical derivation for diffusion through a spherical shell, you will see that they both these terms appear with opposite signs, and I have changed the signs deliberately to show that this is the inward diffusion of hydrogen and gas into the system. So, we can now R0 we have said diffusion coefficient. Now, this diffusion coefficient is different than the diffusion coefficient through the boundary layer. This is the diffusion coefficient through the porous nickel layer. So, we can expect that this is possibly going to be a little lower, smaller than the diffusion coefficient that we have used, maybe 1 order or 2 order of magnitude smaller than what we have used in the previous problem, because this represents the diffusion coefficient of hydrogen H2H2O mixture in the gas phase or through the gas boundary layer. Okay. The density, viscosity, etc. are no more applicable here as far as this equations are concerned. So, this is, we have already found out that this value is 0.09. Value of R is known to us, T is known to us. Diffusion coefficient value, we can use this as a first approximation, noting that this is not applicable, but then the value should be given to us. Okay. Suppose that this value is, I made it as 10 to the power minus 6, that is the value of the diffusion coefficient, and this represents this diffusion coefficient of hydrogen through nickel, solid nickel. But this is exactly not going to be solid nickel, it is a porous solid nickel. There are ducts inside, cracks, etc., through which the diffusion. So, the diffusion actually in solid compact dense nickel is much smaller than this. Okay. and but hydrogen gas diffuses because the size of the hydrogen molecule is very small. So, it can diffuse a little faster. So, with a smaller value we can work it out as a first approximation, and so we can substitute the value here. R 0 we have already obtained, R 0 is the initial diameter 0.143, and then R I we have obtained is 0.00394. So, we will write that the rate of hydrogen reduction is equal to 4 times pi, which is 3.142, multiplied by diffusion coefficient, which I have said that I will take it to be 7.1 into 10 to the power minus 6, okay. And then we will take R 0 into R I, that is 0.005 multiplied by 0.00394, and this is 0.005 minus 0.00394, that is the radial function, okay. So, first component is here with the diffusion term, second is with R 0 R I term is here, and multiplied by this is the 0.09, that is what it is, okay. And of course, we will have R and T, okay. So, therefore, multiplied by this, and if we do this, okay, and then divide by 82.06 into 10 to the power minus 3 into 973, then we get a value which is of the same order of magnitude, but little different, okay. And this value comes out to be 1.93 into 10 to the power minus 8. kg mole per second. Simply plug in the values. So, you understood 4 multiplied by pi multiplied by diffusion coefficient, then this is multiplied by R 0 into R I divided by R 0 R I multiplied by the concentration difference in terms of partial pressure divided by R and multiplied by T. And if you just do this, this is the value that you are going to find, and this is the value applicable. This is what the rate of this rate of reduction is applicable at f is equal to 0.5. So, you will find out that if you change f is equal to 7, for example 0.7, you can understand R I value will come out to be different, and as a result of which the rate will also come out to be different, okay. Now, the last bit of exercise is we have dealt now two independent processes, that is boundary layer mass transfer as well as chemical reaction, diffusion process is the rate limiting. Now, we want to do, for example, boundary layer and chemical reaction together, a mixed control phenomena, and in that case how to deal with the problem. Still it is the same problem, we are making it, I am solving this. So, we know every problem which comes with iron oxide reduction or any other similar phenomena, whether it is boundary layer mass transfer control or whether it is diffusion control, if the geometry is spherical, the same kind of treatment would be applicable to you. You have to be careful about correcting the gas volume up to the temperature, etc. Okay. Similarly, if the mixture density is not given, by applying the continuum laws, how can you determine the mixture density. So, all these small nitty-gritty should be known to you, but nonetheless, as far as the rate of the process calculation is concerned based on one single kinetic step, whatever I have discussed so far will suffice as far as individual steps, either diffusion or boundary layer mass transfer taken as rate limiting kinetic steps. Now, the third possibility here is a mixed control. So, we are saying now that no matter where is the interface, we are saying there is interfacial chemical reaction, and we are saying, look, case 3 is what? When boundary layer mass transfer in conjunction with chemical reaction determine rate of reduction. So, that is the task that we would like to calculate. Okay? I will just take 2 minutes and then I will wind it up for today, then we will continue in the next lecture. Now, so the diffusion does not exist. The diffusion does not exist means that this concentration, okay, and this concentration are identical. But remember, we can no more say that this concentration is equal to the equilibrium concentration as we have done in the case of case 2, when diffusion was the rate limiting step and we considered the chemical reaction to be infinitely fast and therefore approaching equilibrium or essentially at equilibrium. And based on that delta G naught value, we have calculated the equilibrium concentration and specified the concentration, but we cannot do it now, okay, because chemical reaction itself is rate limiting. So, therefore, this concentration is not known to us. So, that poses a big problem here, but this concentration we must understand that see we have a chemical reaction rate. The chemical reaction will see this particular concentration. Then we have a mass transfer which is determined by this concentration and this concentration. This concentration is known as the bulk concentration, but this concentration, as I have said, because diffusion is not there, we will have this concentration and this concentration identical. So, this concentration differential drives the boundary layer mass transfer process with this particular surface concentration being unknown. Similarly, this concentration drives the chemical reaction process and this concentration is not known. But we must understand that whatever gases gets transported through the boundary layer, it immediately reaches here and then the chemical reaction takes place. So, we have a chemical reaction rate as well as the molar rate of hydrogen consumed because of chemical reaction is approximately going to be or very approximately going to be equal to the molar rate of transport of hydrogen through the boundary layer, because these interfaces really do not have a capacity to contain large volume of hydrogen. So, whatever hydrogen is transported by across the boundary layer, that hydrogen is available right up to the interface and therefore, the rate of the chemical reaction is going to be closely equal to the rate of boundary layer mass transfer, and these two equations will provide us a way to circumvent this particular concentration and express the entire phenomena in terms of only the bulk concentration which is given to us in the problem. So, we will discuss and conclude this third case in the tomorrow's lecture, and then it is going to be clear to you that how really this interfacial concentration is. There is a theory is of course discussed in metallurgical kinetics course, but I will write down the final expression, and we want to calculate a scenario when we say that the rate constants here and the rate chemical reaction rate constants and the boundary layer rate constant, transfer rate constants, they both have equal magnitude. Given all the data that we are given here, you should calculate now, calculate the rate of reduction when the boundary layer rate constant and the chemical reaction rate constant are approximately similar order of magnitude value or identical value. Under that case, how can you calculate the rate of the reduction? That will be outlined in the next lecture.